This is Pintu Sa. I have completed my BTech in Mechanical Engineering from JNTUA. Currently, I am working as a application engineer in Paanduv applications from past 1.5 years. So today I am going to demonstrate about our software AM PravaH, where we have exactly matched the experimental result with the simulation result. So the today topic is the process parameter optimization for melt pool evaluation in laser powder bed fusion of Ti-64 using AM PravaH. So AM PravaH is additive manufacturing software, and it has the basically four-phase multi-phase system. So it covers the solid, liquid, gas, and vapor. Now let's discuss on the what I have done in the AM PravaH. So this is the process parameter which I have taken. I have simulated in AM PravaH for the LO is Ti-64 power. I have taken three different power. I have taken 350, 300, 250, and 200. The scan speed is 1.5 meter per second. Powder morphology is spherical. Powder size is 18 to 85 diameter. Spore dia is 100 micrometer. Layer thickness is 40 micrometer. Substrate height is 200, and chamber pressure will be 1 lakh Pascal. So the main aim to investigate the effect of the laser power, or the main aim is to investigate the effect of laser power on melt pool geometry in the LPBF process using AM PravaH. The process parameter, as I had already described, we have taken the Ti-64 material. Spore dia is 100 micrometer. Laser power will be 200 watt, and the scan speed is 1.5 meter per second. So after that, first, as I already describe in the first slide, where the first substrate will be there, above that powder will be spreaded. So as you see that, as you can see here, the powder is spreaded over the substrate. That the powder size is 18 to 85 micrometer diameter, and the initial chamber press initial substrate temperature is 320 Kelvin. And this is the top view of the spreading at the medium fidelity simulation. So process parameter, in this AM PravaH also we cannot directly go when the print exact the parameter with the exact melt pool width, and for that we need to optimize the parameter, or you have to calibrate your system. So for that for, uh, we need to play with the Fresnel coefficient, absorption coefficient are be there, and you can, after calibrating with that, then the result can be obtained from those process parameter will be going to get match with your experimental results. So I have taken this paper for validate our AM PravaH, and after that I had calibrated my software by changing the Fresnel coefficient and absorption coefficient. So this so in experimental is, you see that the power is 300 watt, speed is 1.5 meter per second, and then melt pool width and depth is 97 micrometer and 45 micrometer as per the experimental. After calibrating my system, so I had calibrated where SL calibrated from 0.05, LG 0.25, LV is 0.25, and SG is 0.9, and liquid absorption coefficient is 10,000, where the power and speed scan speed is the same. And after that we had got the same almost close, or close the melt pool width and depth. So I had performed the four simulation in our AM PravaH software, where by varying the power, where the power is 350 watt, 300 watt, 250 watt, and 200 watt, where the experimental result they have reported their width and depth. And then after simulating the AM PravaH software, I had reported this width and depth, which is error in the first. At the 350 watt I got in width 2.94% of the error, and then in depth 6%. So and so on, it is going on. So yes, we can say that our AM PravaH simulation has a very close result with the experimental data. So you can see here. So after that we can, what are other things we can see? So we can plot the thermocyclic part. So I had plotted the thermocyclic plot for all four different powers. So for 200 power, when the laser first hit on the powder, So at that time you can see the temperature is 3100. So as for 250 watt the power is nearly 3300, and then 300 watt the power is more than 3200, and again if you goes for the 350 watt the power is nearly 3800, 3900. So as I told you that, so M PravaH is completely aligned with the completely match the result with the experimental result. So as you see that, see here the melt pool shape comparison, we are comparing the melt pool shape. So this the first figure shows is the shows experimental one, and then the second one is AM PravaH simulation, where we can see the 200 watt at the 200 watt the experimental melt pool, and that simulation melt pool is shown the close alignment between both of them, and so on goes for the 215 watt, 300 watt and 350 watt. So similar way I had taken the slice on the build, and where we can see the close alignment with the experimental one at different power. So the data for the single male pool at the 300 power, so you can see here the experimental data where it is reported is width is 97 and depth is 45, whereas in M PravaH it is reported 91 and 47 of when the scan speed is 1.5 meter per second and power is 300 watt and spot dia is 100 micron. So this result shows that the M PravaH is very much close alignment with the M PravaH shows the very much close alignment with the experimental result. So this is the graph which I have plotted for the experimental VS simulation result. So the schematic diagram for the melt pool and its dimensions. So you can see here the blue experimental width and green one is the experimental depth, whereas saffron is the simulation width and on the simulation depth with the different power. The power is varying according to that we can the width and depth also varies. So this we can see the evolution of the temperature gradient and the fluid flow of the Marangoni convection in the initial stage. So it is the full part, and among them half part is there. So this is a full the fluid is moved from the lower surface tension area to higher surface tension area. So yeah, in this is the final part which got printed with the help of the M PravaH, where you can see the initial stage, that initial stage, and then the final almost at the final stage. So at this yellow white region you can see that the highest peak temperature will be there, and you can see the how the melt pool is forming, and this when it is get solidified you can see here the necking also forming. So yes, we can say that M PravaH can predict the different kind of the defects with the change in the temperature distribution and surface morphology of the melt pool, the single track scanning with the time. If you simulate with the help of the M PravaH, it help you in the cost saving. So it will reduce your cost up to 60 to 70%. Yes, thank you. Have a nice day.